And oh my God, I forgot to bring out the inelastic colliding cars to show you how this works. So we're just going to have to draw it. Or I could, and I'm out of notes too. And I could run and get them. We want to go get them. Okay, 30-second break. Let me go get the cars. Let me get the cars if I can find them. 30-second break. Where are the cars? Oh my God. Okay, that was real. Yay, the collision cars. Here they are. You're all still here. Okay, good. Let's see. So what we have is, we had a good question about, so here they are. There's no friction. There they go. Look at that. Wow. Okay, so how do we make an inelastic? How do you make them stick together? Velcro. All right. To you, Velcro is this old thing. It was actually invented while I was alive. I remember when Velcro was new. Okay, so we're going to look at this equation and see if it makes any sense. We're going to see if it makes the right predictions, because it usually does. Okay, so those two things have the same mass. So let's do a few cases and see if we can plug it in. Okay, here we go. All right, so let's say we have the same mass, and it should slow down by a factor of 2 when they hit, right? Because let's plug in the equation. VF is what? If we initially have just one moving at VI and the other not moving, then it would be M over VI over what? M plus M, 2M. So it should slow down by a factor of 2 if they just crash into each other and stick. This is only if they stick. All right, here we go. So I'm going to go at this speed. Oh, damn, okay. That's not the good one. Here it is. This is the... Okay, yeah, these match. These are the two masses alone in the universe that are destined to be together. Here we go. This is the love story. Oh. There, it slowed down by a factor of 2. Now we're going to go fast. It slowed down by a factor of 2. Wow, it worked. Okay, what if we have them come together at the same speed? See, physicists are into love stories. We're not as repressed as you think that we are. I once knew a physicist that loved her husband so much, she almost told him. That's how, so V1I and V2I is that way. So let's say they're going in the opposite direction, same mass, and same mass but opposite direction. What are we going to get? VF. Let's plug it in. These are components now. All right? So this one, we'll just say it's going at V. Or just, well, the point is they're going the same. So I'm getting to the same subscript. They're both going at VI, just different directions. But since this is a component, let's do magnitudes. Sorry. Okay, so now this is a problem where we know the initial sides. We're going to put magnitudes into this formula, but we're seeing the sign tells us this side. So this is a component. Okay, this is why these problems are tricky. The algebra is not hard, but keeping up with signs is tricky. So as I say, sometimes you do magnitudes, sometimes you do components, sometimes you kind of mix it together. Okay, and you have to, because if we just do components on this side of the equation, we're never going to capture the fact that it's moving this way. But then we're going to let the sign tell us what's going on here, if there is a sign. Because in this case, we have m times vi component minus m times magnitude minus m times vi magnitude over 2m. Of course, this one is 0, right? Because these two parts cancel. So if I send them at each other with the same velocity, after I let them go, you're going to shout out the total momentum, the numerical total momentum. You're going to shout it out in any unit. 0. Yay, and it stayed 0. Look at that. The total momentum is 0. Whoa, 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 it's still 0. Still 0. 0. It's never changing. 0, 0, 0, 0. Look at that. Woo-hoo. Oh, shit, now it's not 0. Okay. Now you see how it works. That totally made sense, right? Are we still going? Okay, so let's do another case. Here we go. I have like detailed lecture for the next part, but I figured doing these examples might be better. Let's just do one more. And let's think about what if we make their masses different? Now it's going to get interesting. I planned this way ahead here. Okay, so now that would just slow down more, wouldn't it? Okay, so if one weighs more and they come at the same speed, which way is it going to go? Let's plug it in real fast. The heavy one hits the light one. M. Let's say 2m. But they're both going at VI, same magnitude, like that. Let's see if we can plug that in and see which way the whole thing is going to go. So we'd say VF equals, this is M, magnitude VI is positive, minus 2m, magnitude VI is negative. So the magnitude of VI, I put the negative on there because it's going negative, over 3m, right? 2m plus 3m. So you can see the answer is negative. It's going to be negative 1/3 VI. So if that really did double the mass, which is approximate. But the point is, it should go this way. The heavier mass will win, and it will go that way. So here we go. Oh, yeah, they're both going. Oh, shit, they're both going at the same direction. Oh, this is not going to work. Okay, here we go. Did you see it started to fall that way? Okay, same direction. There we go. It went that way. I have other masses, but I don't want to leave again. Oh, I could have put this on top of it. Okay. Oh, well, here we go. 2m. I am an experimentalist. Here we go. There we go. So it slowed down. You couldn't tell exactly 1/3, but it did slow down. Okay? So that's examples of the conservation of momentum.